All right. Hi, everyone. My name is Dr. Joseph Nesri. I am an associate professor here at Rice University. Welcome to the International Methods Colloquium. The International Methods Colloquium, or IMC, is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Rice University and the National Science Foundation. This week's speaker is Adeline Lo, a postdoctoral research associate at Princeton University. Her talk is entitled Making Good Prediction, a Theoretical Framework, and this is based on work co-authored with Herman Chernoff, Tian Zhang, and Xiaohua Locke, with my apologies if I messed up any of the pronunciations of those names. Adeline's talk will last between 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And you can ask questions anytime, but we're going to hold anything except the most clarifying questions to the very end. A link to Adeline's paper and the slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation. I will send out those links just as soon as I'm done with this little introduction. And now I'd like to welcome Adeline Lo to the International Methods Colloquium. Welcome.
Hi, everyone. Thank you so much, Justin, and everyone at the IMC for having me here today. As Justin just said, this talk is on good prediction. It's ongoing work, though this portion has been published, that I've been working on with a few of my co-authors for the last few years. So without further ado, I'll kind of just jump into it. So we know prediction is important, but I'm going to kind of try to motivate it a little bit more, especially for the social scientists out there. So we wish to forecast things like violent events, civil wars, revolutions, local conflicts. We might also wish to predict somewhat difficult things like economic recessions or good times, bad times for the economy. More and more, as our data has become more complex and we've been gathering sort of every kind of data from text to genome-wide data, it's become both more complicated in the sense that there are more variables that we have to consider, but also we wish to predict more complex things, such as maybe disease status at the genome-wide association level. We also actually use prediction a lot in causal inference techniques already. So most of us, if we're applied workers of any sense, probably have predicted at some point or another. For instance, we might wish to select among many and possibly very weak instrumental variables in two-stage least squares. We might wish to construct synthetic controls in difference in differences designs. When collecting interactions in conjoint analysis, we might also wish to predict in order to collect the interactions that are most predictive for the outcome. This may also click in for finding fewer interactions of factors in a factorial experiment, or simply just predicting case control labels if we have text data. And we know that text data at this point can be anything from millions and millions of tweets to tons and tons of blogs that are scraped off of the internet every few seconds. However, not nearly enough attention, we think, has been focused on creating a framework from which to theoretically consider predictivity. So why does this matter? First, creating measures of predictivity specifically through the lens of maximizing theoretically correct prediction rates, or at the same time, minimizing theoretical error rates, this might be important for better prediction. Now you might think, can we just use models or methods that seem to predict very well, regardless of how they were motivated? So one motivation we had for this project was on working on the statistical properties of the influence score, this I-score, that we will suggest here as a good measure for predictivity and its performance in particularly complex and high-dimensional data. And we actually believe that the I-score's strong performance is because the score itself is related to, and I will show this in a few slides, to the theoretical correct prediction rate. So there is reasoning for why it is that this method seems to work. And there may be logic to and benefits from the creation of prediction measures from a prediction framework. So currently, there are several sort of main approaches to prediction that we see. The first in at least the social sciences is to collect theoretically known important, significant variables, and to use those to predict. So for instance, we might think that the capability to mount an insurgency, mountainous terrain, or ethnic fractionalization, variables that we have hypothesized as social scientists as important when relating to civil war, we might use these to go and then again forecast the civil war. Another sort of common approach is to use out-of-sample testing or cross-validation. So we take all the information we possibly have and we fit as many models as we can and try to just find the model that has the least error in out-of-sample testing. And this we sort of focus on as our best forecasting model. We show in other work that actually using the significant variables approach to selecting variables to predict doesn't necessarily guarantee you high prediction rates. And actually the reverse is also true, that highly predictive variables might not show up as highly significant. With regards to fitting many, many models and considering whichever one sort of does the best when it comes to error rates, currently we find that there doesn't seem to be as much of a theory-based measure for the underlying predictivity. It's really just, does this model predict well? Do these variables seem to predict well? So we don't know necessarily why it is that certain approaches tend to perform better than others in some scenarios. And it's hard to find a benchmark against which to compare. And both of these approaches additionally suffer from the curse of dimensionality constraints. So what that means is as our data grows sort of in the standard way, if rows are observations and columns are variables, as our matrix grows sort of outwards with many variables and our observations sort of doesn't grow as quickly, then if you think about all the different variables that could interact to then predict, this dimension grows exponentially. So we believe that our contribution here is a theoretical framework from which to consider prediction. So we try to set up this idea of what our objective function should be. So what are we trying to do here? We're trying to measure how predictive a group of variables might be for a given outcome. We then try to maximize this objective function and find a solution. So what is it that we can use to get at high levels of predictivity? And then, which I'm going to explain later, we try to find sample appropriate measures for measuring this predictivity that match this theoretical solution as closely as possible. So I'm going to discuss this a little bit in a bit, but the solution of this objective function in the sample framework doesn't actually have a usable analog form. So our second contribution stems from considering an alternative solution where there is a sample analog that is usable. And this alternative solution is going to be directly related to the maximizing of the objective function. So I've sort of been talking about maximizing predictivity, but what precisely does that mean? And what is an influence measure that measures predictivity? What is that supposed to look like and what should it do? Well, first we think that it should reflect the predictive power of a given variable set. It would be nice to be able to handle also groups of variables so we can accommodate the interactions of these variables. It's also going to be really important to be able to differentiate between actually influential variables and noisy ones, especially as the number of variables grow. So I'm going to start with a sort of a simple example. We're in the simplest of worlds. We have one explanatory variable, X, which I'll call democracy, and an outcome variable Y, which we'll call civil war. Both X and Y are going to be binary for the purposes of here. X is defined on a space pi X with a density Px of little x. And the civil war observations I'll call N sub D, and no civil war observations or peace observations are N sub C, each with their own two probabilities, Pxd and Pxc. Then the expected correct prediction rate, C, using variable X, democracy, is some constant times the absolute difference between when X is 1 of the probability of Xd minus the probability of Xc plus the absolute difference between when X is 0, or there's no civil war, of the Pxd and Pxc, and adding those two together. We can call this the predictivity of variable X for variable Y. Now we're going to imagine that we have tons and tons of X variables, which is more realistic. Then what we're looking for is a subset of these X variables that maximize the correct prediction rate C. So given that I have collected some number of X variables, and I don't know which ones are actually the most helpful to forecast a civil war, then I want to look for the subset that has the highest correct prediction rate. Here, the correct prediction rate with this group of X variables, which I'm going to use boldface X for as a discrete random vector defined on space pi X again. Again, I have ND cases or civil wars and NC controls or no civil wars. And these are independently selected from two discrete probabilities. Again, PXD, PXC. These two XD, XC discrete random vectors arrive as a pair when your X variables are fixed. And they're also defined on a Karman partition space. So if a new observation has a 50% chance to be case or control, so our prior is a 50% chance, the expected correct prediction rate or error of adopting this rule is C is equal to 1 minus the error rate. So that's the correct prediction rate is 1 minus the error rate of 1/2 the sum across all of the X's in that partition space, where we maximize the two probability distributions and sum it up. So this is specifically for the situation where we have case control, and we have this equal losses for errors on either side. Then the correct prediction rate can be shown to be 1/2 plus 1/4 that sum absolute value difference. We also have a sort of different notations for when the observation prior is not 50%, and also relaxing for when the losses are different. But for the purposes of this presentation, I'm going to focus on 50-50 chance prior and the losses are equal. So we'd like to then estimate equation 1. We'd like to get the variables, the X's, for which this C is as big as possible. So that's our goal. However, the sample analog of this particular C is always increasing in variables. So as long as you add more variables, it always goes up. And so it isn't able to satisfy that requirement that we'd like for a statistic that's helpful in predictivity, which is to separate between influential and noisy variables, right? Because it's going to, regardless of whether it's influential or noisy, always increase the C hat, let's say. So this sample analog is not something we can actually use. What is it that we can then use? Well, I'm going to first introduce a very simplistic lemma. Let A1 through AK be K non-negative numbers. Then if I sum A sub I from 1 through K, that's going to be greater than if I take the L2 norm, which is the square root of that same summation except of AI squared. If we replace AI by that absolute difference of PI given D, PI given C, which is just the probability XD, probability XC for all I's, then it's clear that if we maximize the right-hand side or the summation of that squared term over the possible pairs, we're going to have the same parallel effect of encouraging the selection of pairs that maximize equation 1, yielding a better predictor. So this is going to be essentially a lower bound on that absolute value difference that we showed to be the correct prediction rate. We can show that the I-score can be seen asymptotically as precisely a maximization of the term up to a constant of the summation of PID minus PIC squared, so the L2 norm. Since this is a lower bound, then a strategy that seeks for a variable set with this larger value of this lower bound will have the effect of seeking for the variable set with a better prediction rate. But again, this will be a lower bound. So the intuitive explanation behind why it is that this statistic might be helpful is that the absolute difference is strictly positive linear, and increasing in the positive space of integers. But the squared term allows for the existence of a maximum. So let me talk a little bit more about what precisely this score looks like. Suppose I have n observations of my outcome civil wars or no civil wars, and a large number S of my X variables, my explanatory variables from X1 through XS. If I were to randomly select a small group, M, of these X's, and I call these MXJ, where J can go from 1 through M, and it can take discrete values here in the example, then I have M sub 1 is 3 to the M possible values for each set of X's. So if I take 3, I have 3 to the M, that possible values. Then I'm going to take my N observations and put them into the M1 cells according to what values these M observations have taken, these observations have taken in the X's, and refer to this partition as pi. So the score is designed to place greater weight on cells with more observations. And so the score looks like, for I of a given pi, it's the summation from k equals 1 through M1. These are all the possible values for each set of X's. Nk, which is the number of observations in each k cell, over n, which is the total number of observations, times y bar k, which is the average value of y in each given cell k, d-meaned by the global average of y squared, and then divided by a variance term. So this, you might look at it and kind of see maybe some familiarities with the chi-squared. The Pearson chi-squared statistic is actually quite similar looking. It has the observed minus expected squared. However, a key difference, which is going to sort of be most of the work here in the statistic, is that we're going to weigh each of the cells with the number of observations that occurs in the cell. So what we're saying is essentially, we want to look and focus on where the data actually is. And when we have very, very sparse data given these partitions, then that's really where we want to focus. So I'm going to motivate a little bit more of the I-score with some asymptotics, and then I'm going to talk a little bit about how the score fares under data simulations. So first, as n approaches infinity, as our observations increase to infinity, the I-score can decompose to a term that looks like the following: a constant times the summation of j over all of the partition pi, pjd minus pjc squared. And so this might look a little familiar to you. If you recall the correct prediction rate, it's c equals 1/2 plus 1/4, and then this absolute difference, value difference. So the similarity can already kind of be seen in the sense that the I-score is going to be, again, that lower bound L2 version of the theoretically correct prediction rate that we're trying to maximize. So in the sample world, what we're going to look for are sets of variables that seem to have very, very high I-scores when compared to other sets of variables. So then how does the I-score fare with data in a sample constrained world? In this example, the x-axis are the x variables. X variables are from x1 through x12. Variables that are in black are noisy, and variables that are in red are influential. So in this case, we have 3 out of 12 variables that are influential and 9 out of 12 that are just noise. And the influential ones are in red. The y-axis is the correct prediction rate. And from left to right in the panels, we increase the n size, the observation size, from 500 case control, 1,000 case control, 2,000 case control. If we look at the reference, which is the out-of-sample prediction rate in the light blue, in each case, the out-of-sample prediction rate is highest or maximized at x1, x2, x3, which are the variables that are actually influential. So this is in the sort of perfect world where we have infinite samples, and we can kind of sample forever and take a look at and estimate the prediction rate. So in this case, adding noisy variables decreases this sort of impossible to achieve but perfect world of infinite sample data. If we look at a training set prediction rate, this is the problem that I was referring to in the sample analog version of C. So trying to measure C by C hat with real data. The problem becomes that in adding any kind of variable, in this case, the noisy ones, which is sort of the worst scenario, our training set prediction rate just keeps increasing with the addition of these variables. The I-score is in red, and it can be seen that it's, again, this lower bound. So even it's below the light blue in these violin plots. But it is maximized at the point in which you have the most, when you have your influential variables. And so it drops with the addition of noise. So that's something that we kind of want, what we're searching for in statistics for measuring predictivity, right? And that's not to say that the score is the only sort of possible statistic. We actually think that there are probably lots of different ones that haven't been designed yet or haven't been explored yet. But this is sort of one of the qualities that we'd really like for our statistics to have, which is to be able to separate between influence and noise. With real data, what we've used the score on have been sort of a variety of data sets, but I'll focus on this one for now, which is the very well-known Van Devere breast cancer data set. It's been well studied with tons of variables and very few observations, because these are patients who either have or don't have expressions of breast cancer. And the literature-wide error rate had been lowered down to the point of 30%. And we were able to lower that further to 8% with the identification of highly interactive genes that were able to be extremely predictive for these breast cancer expressions. And so we might see that if we were to try to use a statistical significance approach of finding these genes, for instance, this set of genes, a set of 5, which we found to be highly predictive, considering their marginal p-values, given the family-wise threshold, or the joint p-values, we wouldn't have been able to find them. Whereas the joint I-score of 2.89, which is significantly larger than 1, which is the null, let us know that this was something that was important, and we should focus on it because it was much larger. So this is all to say that there are several desirable properties that we find of the I-score, and we think that this can hopefully open up an avenue of research into thinking about statistics that specifically cater to estimating predictivity. And so maybe the I-score is not necessarily even the best one out there. It's just the only one that we've sort of been able to really spend some time on developing. And so the first thing is that it doesn't have a model specification for the joint effect of a set of X variables on Y. The score captures the discrepancy between the conditional means of Y on these variables and the mean of Y. So that was the sort of the YK bar minus Y bar, weighted by the number of observations. There's also this differentiation between noisy and influential variables. I doesn't monotonically increase with the addition of any variables, which is something that the sample analog form of that equation, C, suffers from. Rather, when we have a given set of variables, M, with M minus 1 truly influential variables, I is higher under the influential M minus 1 variables than under all M. So dropping the M minus 2 variables leads to a decrease in I. And so I has a natural tendency to peak at variable sets that lead to the maximum predictive rate in the face of noisy variables under some constrained sample size. We've also shown that the approximation of that I approximates the equation 1 by identifying a cluster of variables that maximizes the L2 norm, essentially, version of that probability difference between cases and controls. via the squared term. So this is directly related to the maximization of the correct prediction rate, but from a lower bound. And elsewhere, we've also shown that I is able to handle interactions of a higher number. So we believe we should rethink how we approach prediction. First off, we think that variable selection cannot be accomplished through a mainly significance criteria, simply because we might be choosing variables that are highly statistically significant, but are not necessarily highly predictive, which in this setup is our goal. We might require new measures and new criteria that are in fact prediction-based, and we think that this is a really interesting and new avenue of research. And so we preliminarily offer this I-score, which has the following nice properties. This relationship, theoretically, to the maximization of prediction rates. It seems to predict well in simulated and real applications. And it can distinguish between noisy and influential variables in a sample constraint setting, as well as handle interactions. So that's basically it. I'm happy to take your questions at this point. And thank you so much again for partaking and having me here.
All right. Thank you, Adeline, for that presentation. At this point, Adeline Lo is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of the webinar window. And a few questions have already come in, so I'll start giving you those, Adeline. Mm-hmm. So first, Thomas Paul has actually asked 3 questions, so I'll just ask them in order here. First, how would one distinguish variable influence from the relative importance of variables? And I think this is coming out of the machine learning literature, where you can get these various relative importance measures that come out of certain models. And a related question is automated approaches such as deep learning neural networks claim to have workarounds to finding useful and important covariates, their interactions in lag order. For exploratory purposes, is this enough?
Sorry, so I just want to fully understand. The first question is distinguishing between influence versus relative importance?
Yes.
Okay.
How would one distinguish variable influence from the relative importance of variables?
So I'm not particularly sure if this is in reference to, for instance, something like the relative importance in random forests variables.
That's what I was thinking of, yeah.
Okay. So I think in this case, what we're looking at is, in particular, when I say influence, I should be really careful in saying that what I mean by influence is high predictivity, so that it is extremely predictive of the outcome variable. And so I think for the relative importance scores, it's looking at some comparison between the variables themselves in the splitting of the trees. And so it's not quite the same thing that I'm talking about, which is evaluating based off of how predictive these variables might be for the outcome. So it's a little bit different in that sense, because I'm not comparing necessarily a group of variables directly against another. I'm evaluating the prediction rate. And then, of course, after that, since you have the prediction level for a given variable set, you can then compare. But the score isn't constructed with that comparison in mind. And then for the automated approaches, the deep learning workarounds, I'm sorry, do you mind repeating?
Yeah, I'm happy to repeat it.
Yeah.
Automated approaches such as like neural networks claim to have workarounds to finding useful or important covariates, their interactions and lag order. For exploratory purposes, is this enough?
So I think for neural nets that are trying to predict that are trying to create classifiers to predict some complicated images or whatever outcome it is that you're looking at, the goal is similar. It's trying to find the model that best fits for best prediction. But this falls in the category of what I was discussing in the beginning, which is sort of just trying to fit models that, however they might work, however those covariates might be weighed or used in different functional forms with one another, whatever model comes out best for our prediction rate is the one we use. And what we're trying to say is, well, let's back up a little bit more before that and just try to evaluate, even before we throw in all the variables. Let's try to reduce that number by focusing on selecting variables that might have some promise already. So this is in the situation where we have high dimensional data of millions of SNPs or hundreds of thousands of Chinese characters in blogs that we have to evaluate. And what we want is to maybe reduce that size. So then just variable select for words or for SNPs that have some promise. And because we have that selection process, we then know a little bit more about which particular covariates are promising. Whereas in the neural nets approach, one difficult thing for many users is that it's hard to tell which and how much of the variables are actually sort of going into the final model. And secondarily, it can be really difficult to run that neural net when you have way too many variables even to consider, given the number of observations that you have. So we see this as a sort of almost screening step that you can take when your data size is just a little bit more on the unmanageable side because of the variable to observation ratio.
You know, I'm trying to get a handle on some of the practical issues that would be involved in trying to do something with this in a project. And I'm looking, for example, you don't have to go back if you don't want to in your slides, but I have your slides pulled up. This is why we shared the link, right? So people can look back at the slides. So I'm looking at, slide 17 where you're talking about 17, 18, 16, 17, 18. No, they're all the same, 17 out of 26, where you're talking about how you would use these scores. And I'm thinking, okay, if I've got a large number of X's and I'm partitioning them into some sort of table like this and computing essentially a version of a chi-square score, the initial problem that comes to mind is the curse of dimensionality, right? Most of those cells are going to be empty. And that's a huge issue, like on a variety of different levels, right? Why isn't that, I guess what I'm asking you is, can you explain why that's not a problem for your approach in given this methodology? So
I think that's a great point. And I'm glad you brought it up because then I can kind of go to it because I don't think I spent enough time on it. So that's a problem that's going to plague all researchers when you just have too few observations, way too many explanatory variables. And so any way you cut the data, it's just going to fall so that you have cells with mostly nothing in it. So the reason why we take the approach that we do, which is to subset the number of variables and then calculate the score, it has benefits and drawbacks. So the drawback is that we're not going to be able to calculate something like a 100 variable interaction for the outcome if you only have 500 observations. Right? That's not going to be possible if you have, and each of those variables have 3 to 4 levels and you sort of create that partition, you're going to see mostly nothing. So there is going to be that constraint. What we suggest instead is to take that random small group of M to be something that's manageable, but still interactive. So you have 200,000 SNPs. To do even 3-way, 4-way interactions would be incredibly difficult with a lot of standard methods without reducing that variable set. So randomly select many, many times an M of size 6 and then calculate that partition. And it's going to be a little bit more doable. The thing is, the benefit of it is that we're going to be able to calculate the I-score. It's one score for each partition, right? So we're going to be able to just calculate over and over as many times as your computer can calculate a single statistic, right? Many times. And we have software that we're making available for people to do that. So you just calculate as much as you can and as long as you want. The benefit is that you're able to do it up to whatever your starting small group of M size is. So that can be as high as 6, maybe higher if you have more observations given your variable size. The drawback is going to be that you only can find up to 6 or 7-way interactions given from where you start. But we think that this is already a major step up, right, in being able to find interactions in a much sparser environment.
I mean, one question that just came up, and I think I'd like to ask a version of it too. So a question that came up is if you could compare and contrast this approach with other methods such as partial least squares. And what I was thinking was, I'm teaching Bayesian statistics right now, and I was just teaching stochastic variable selection and Gibbs sampler selection, and sort of variations on the Bayes factor, where you try to make the Gibbs sampler pick out the variables that are the most important, and it searches through a big space, basically by the way Gibbs sampler searches any complex space, right? By sort of sampling. Why do you think that? How do your techniques compare to these other sort of more established techniques, and why do you think that your technique will be more efficient or in some way better?
So a lot of these approaches are doing two things at the same time. The first is that they're doing screening, and the second is that they're doing model fitting. And so when you do something like a lasso with different types of penalization, or if you're doing doing a neural net, any kind of like deep or not neural net, then the algorithm is already selecting for variables, but also at the same time fitting it to some sort of function that then is supposed to map to that outcome for whichever it is that you're trying to predict. Here, we're not trying to do the model bit. It's meant to serve only as a screening. So I guess a comparison that would make sense would be Shor independent screening. So it would be evaluation under high dimensionality, and then proceeding with the model of your choice after making the variable set more reasonable for evaluation. So in that sense, I guess that's why it's slightly different.
I want to follow up on that. So I try not to promote myself too much on these things, but this is actually really relevant. I wrote a paper in political analysis a couple of years ago where I was comparing classification approaches of model fitting and assessment to probability-based approaches. And my concern was that for a lot of events that we study, like Civil War outbreak, for example, my thinking was that's not something that actually is knowable in advance. It's not a 0 or a 1. It's a probability. It's more like a dice roll. And when I want to figure out whether a model is fitting the data well, both in sample or out of sample, right? I was concerned about out of sample. What I really want to know is are the probabilities correct, right? If I say it's a 10% chance of happening, it happens 10% of the time, which is different than a classification-based approach where you say, well, there really are ones and zeros, and basically what I'm trying to do is maximize the degree to which I can sort out the ones and zeros. And it seems like your approach is really more of a classification-based approach, right?
Yeah.
There are ones and zeros. So to what extent, that was a long-winded question. That wasn't really a question, that was a comment. Now my question is, do you think your method could be extended to these problems that are common in political science where maybe the DGP is not really a classification DGP, it's really more of a probabilistic DGP? So
I think the short answer is I think it probably could, but it would require some rethinking on the way that we set up the C equation. Because from how I see it now is the way that we've set it up is so that there is a probability distribution from which you must come if you are a case versus another one if you are a control. And it's going to be different if from what you're saying is it's not necessarily true that it's these two distinct distributions.
Exactly.
Then the way that we would construct, I think would absolutely have to be different. But if we can get to the point where we construct something like a maximization of some sort of probability distribution given covariates, then I think the at least theoretical approach that we take to it should be similar, though not necessarily the statistic that we would use to measure it. Yeah.
I mean, to me, that's really important because I think the reason I wrote that original paper was I think a lot of our problems, the DGP, you can think of this as sort of a toy or a conceptual device. It's really more like a pair of dice with a different number of sides colored red or blue, right? It's not that every observation is either red or blue in advance and we just don't know and we're trying to figure that out. It's more like every new creation of a sample, you roll that dice and an outcome occurs. And what you're really trying to understand is the dice that produce that outcome. And so a good fit is to say, well, this particular observation had a 50% chance of an outcome occurring, and I predicted that it would have a 50% chance of that outcome occurring. Not that it was going to happen or not going to happen, right? It's kind of trying to classify dice rolls would be a bad idea because we know they don't exist prior to the roll, right? There's aren't ones and zeros. I think that'd be to me as a political scientist, I think that'd be a really important extension because so many of our problems are like that.
And I think the hardest part when it comes to forecasting is ultimately we are most convinced of the approach when we have data to validate. And it would be, I think the hardest for me would be to find data that could validate that probability as opposed to the event occurring or not occurring. But I think that's something to think about.
That's right. That's what motivated that paper because you're exactly right. And most people are convinced when you say Donald Trump is going to be elected and then it happens, right? That's what people intuitively understand. They're much more confused when you say there's a 25% chance that Donald Trump's going to be elected and then it happens and they think you were wrong.
Right.
Dude, I told you there was a 1 in 4 chance. If I rolled a dice and, 4-sided dice, a tetrahedron, and the blue side came up, you wouldn't say the dice were wrong, right?
Yeah. So maybe, and this is just sort of, I'm just thinking as we go along, maybe the place where I would start considering it in order to, if I had to avoid starting from fresh, would be to think about the loss functions in some way that's different. Because what it suggests to me is that we need a better sense of what is the true loss of, going from a fourth to 25% chance. That should be weighed appropriately. And maybe putting all the weights at 0 and 1 is kind of a place where we're suffering. But I'm not sure.
Well, so I just want to, I think we're about out of questions, but I want to mention a couple of things that Thomas actually sort of following up on his previous thing said. He mentions the random forest is one approach. He cites a particular work by Ulrike Gromping, and she has an R module and rela impo. So I guess that's a contraction for relative importance, is exhaustive in its review of the heuristics relative to relative importance. And then there's a good reference for that in a paper called Deep Learning for Mortgage Risk. So you may find this references important. I think that this is a pretty active area of research, and I think political science, is sort of transitioning into this phase where we're trying to do more out of sample prediction is now being recognized somewhat belatedly as important. So I'm glad to see people working on the question.
I think we're actually pretty progressive and pretty cutting edge when it comes to some of the forecasting work that's been done by social scientists in political science in particular. I think not to toot our own horn, but I think given what we have been interested in, what we think is really important, I think we've long recognized because a lot of our data comes in the form of complicated documents. So we were probably early folks on that ship sailing to high dimensional prediction. So I'm really glad, but I think this particular realm of research is one in which we have, I think, a little bit of an advantage because we've already cared for a long time. We have the data. And so this is pertinent.
Okay, well, wait a minute. One more before we can go. So Thomas says, in my view, out of sample validation provides at best limited information, particularly with respect to predicting the likelihood of unknown future events. A good example of this is the stock market and predicting the future trajectory of a stock.
Yeah, it is the golden standard, I guess, of out of sample validation via future data. Sorry, go on.
No, I was just going to say the question to me there is whether the trajectory really exists in advance. That's a perfect example of something where, I kind of wonder whether it's more like, well, there's a distribution of things that could happen, and what you're really trying to do is predict the distribution, right? Because it's not like there's a future that's sort of laid out deterministically, and we're definitely going to go down that track. I don't know.
So that's kind of the example that most economists sort of fixate on, because it's so hard to predict. I mean, if you were to predict even 50.1% better than at random, you would already be making market gains. That would be insane.
Right.
So that is one of the hardest things, I think, to predict. Now, that's not to say that that I think it's always possible to predict. So I guess I should also back up that example as an example where it could be that the data that we collect can only ever give you a maximum amount of predictive power, and you're not collecting the right things, or you can't. So I think knowing what our constraints are is also helpful. And it could be that in a situation like trying to predict stocks on a day or second by second basis is out of our hands given the information that we have. But maybe we also haven't developed the right tools. So who knows?
All right. Well, I'm going to go ahead and call it. So thanks for everyone. Thank you. Thanks for everyone for coming. Thanks to Adeline for being our presenter this week. I want to mention that your presentation, or her presentation, will be posted to our website shortly after this broadcast, if you'd like to share it with others or watch it again. And I also want to announce next week's talk. Excuse me. Next week, November 17th at noon Eastern Time, we will host a talk from Olga Chiza from Iowa State University. The talk's entitled "A Local Structure Graph Model, Formation of Network Edges as a Function of Other Edges." Please see our website, www.methods-colloquium.com, to get more information about this talk. And we actually have a paper to circulate as well. Adeline, thanks very much for being our speaker today.
Thank you so much, Justin.
And hope to see everyone next week.